it runs at XXX frames per second using MATLAB, where XXX is going to be more than 2 and less than 90,000. So it's in there somewhere. Depends on how fast your computer is. So here's some results that they show you. Now up here, this is the main image, and you can see they're tracking the face there. What you're going to see here is going to be mostly about where the image is being explained best. We're going to talk about that more when we talk about occlusion. And what you're going to see down here are about 10 of the eigenbases, right? And you're going to see that they're changing as the appearance changes. So if I press, there we go. All right, and so you can see that it's doing a pretty fine job of explaining the face, of tracking the face. That middle row that I was talking about, that has to do with what am I seeing versus how well can I reconstruct it from the basis set, and it's using that as its evaluation. And you can see with really large lighting variations, it tracks really well. You saw it got stuck there at the very end, and that sort of as far as it could go. Yeah, here's another example where you're going to see a lot of sort of change in orientation and change of appearance. And this is Sylvester the cat being tracked, and you can see that it creates a lot of really sort of creepy-looking Sylvesters on the bottom. Those are the eigen cats, the images of the thing, and that's how it's doing its tracking. So let me show you something that same group and others pushed on a little bit more recent of handling occlusion. So the question is, you know, if a thing gets partially occluded, we have this problem, because remember the eigenface stuff is it's capturing the entire image as a vector. And all the pixels, all the components in that vector are created equal. So if some of them are sort of being blocked or obscured, it's not going to be able to explain that data. It's not going to be able to track, give you a very high probability at that area. But it turns out you can address that if you think about the following, right? By the way, that's Greg Dudek a while back. Hi, Greg. Picture there. When I reproduce an image, so let's suppose I've tracked this thing, I've computed my eigenbasis, and now I'm trying to find my best one, and I do. I can now say, of all those pixels, which ones am I reconstructing well? The ones that I'm reconstructing well, those are the ones that I have a lot more confidence in. So let me create a weight mask that says, you know, those pixels are fine. But anywhere that I find something that I can't reconstruct well, I'm going to highlight those pixels as ones that I'm not going to pay attention to. By the way, the reason I'm saying highlighted is on the video I'm about to show you, for whatever reason, they have sort of bad pixels as being bright. So you can think of them as being highlighted for not counting as much in the current or the next iteration. So what you're going to see here in this video again is, so here's Greg's face that's going to be tracked. And this is the sort of the location of what they're doing. But what you'll see here is there'll be this black image, and then all of a sudden you'll see his hand swipe up across his face. Now, of course, his hand is not easily reproduced with the face eigenbasis. So you're going to see that light up. And that's it saying, okay, the weight of those pixels should be reduced. So let's see if this works. Ah, there it goes. It's playing. Okay, same thing we see before. You see his eigenvectors changing on the bottom as he rotates in and out of the plane. Whoops, there was his hand. Did you miss that? Let's go back again. Now get ready. In a minute, he's going to swipe his hand over his face. There it goes. Did you see that? You can play it backwards. As his hand came up, the weights got brighter where the hand was, saying, ignore this place. And now it tracks him for a while. He's smiling. He's getting large and moving around. And you can see it's doing a good job tracking. You can see the difference between how well it can be reconstructed. And the reason it can handle things like this is, remember, the state that it's tracking is position, translation, rotation, scale. So you can normalize it back to the original sort of canonical view and explain that view from the eigenbasis. All right, so that's some pretty cool tracking work. It's an interesting example of using PCA, the stuff we just talked about, on image patches. And it's funny, like I said, I couldn't show you this during the tracking part that we did because you didn't know about PCA yet, or you certainly didn't know about it from me. And this really wasn't recognition, but I thought it fit in well here because now that you understood PCA as a low-dimensional representation, we can use that for a lot of things. So now we get back to recognition. Actually, next time we'll get back to recognition. All right, welcome back to computer vision again. We're going back to recognition now. Remember before we were talking about supervised classification? Supervised classification is I give you a bunch of labeled examples, right? Typically referred to as training examples. And you're supposed to come up with a function that'll label some new examples. And we showed this one where we have a bunch of hand-drawn 4s and hand-drawn 9s. And the idea was, given some new input, is it a 4 or is it a 9? The idea was, since we know what the desired labels are from the training data, we're going to try to build a classifier that's going to minimize the expected misclassification or minimize our risk. All right? And we talked about that there were two strategies. One was called generative, where we probabilistically model each of the classes and then somehow pick them. We'll talk about that again just for a second. And then there was discriminative. And discriminative says, I don't care so much about modeling the classes. What I care about is modeling some sort of boundary between the classes, and that makes it easier to make some decisions. So we talked about the risk of a particular decision as being, if you're making a particular decision, what's the probability that that decision is wrong, and what's the cost of making that wrong decision. So, for example, let's suppose that I'm going to label something as a 4. Well, if I'm going to label it as a 4, what's the risk associated with it being a 4? Well, that risk would be, well, you know, what's the probability that it's actually a 9, okay? And what's the cost to me of calling a 9 a 4, all right? So that's the risk of labeling something a 4, right? Because it actually might have been a 9, and what's the cost? Likewise, suppose I'm going to label something a 9. What's the risk of labeling something a 9? Well, the risk of labeling something a 9 is the probability that it was actually a 4 times the cost of labeling something a 4 as a 9, all right? And where should my decision boundary be? Well, my decision boundary should be that the risk of either decision would be the same. Okay, and that was the idea of the generative model. And so that's what's being shown here is, so here are all my real 4s, so I'm pretty sure that they're 4, so I'm going to call them 4s. But as I'm getting over to the other side, it might be a 9. Here are all my 9s. And as I'm getting closer over here, it might be a 4. And this boundary in the middle, that's where the risk is the same. So to do this even risk assessment, we said we needed to know two things. One is we need these loss functions. We need these costs. Right? Somebody has to tell me, because I can't know that. It's not defined intrinsically in the data. It's the cost of, you know, either societal costs, economic costs, you know, whatever. As I said before, the cost of somebody calling somebody stupid who's really smart and large might be much worse than the cost of calling somebody smart who's actually stupid and large. Think about that one, okay? But the basic idea is that the costs come from outside the data. But the other thing that I need is that I actually need to know the probability that something really is a 4 given some measurement, or the probability that it really is a 9 given some measurement, right? And we need to be able to evaluate those. So the way we did that, if you recall, is that we talked about estimating the likelihood. That's the probability of the measurement, given that it's, here we were doing skin colors, given that it's a 4 or 9, or given that it's skin or not skin. And then how did we go from likelihoods to actual probabilities, posteriors? Well, remember we used Bayes' rule. Okay, and Bayes' rule would allow us to take these likelihoods, right, the probability of getting the measurement given the class, skin, etc., multiply that by this prior, just what's the probability of getting a 4 or 9, or in this case of getting a pixel being skin or getting a pixel not being skin, and you multiply them and you have to normalize them and you get this posterior, which was the thing you wanted. Okay, and that's what this equation down here says. The probability of skin given x proportional to p of x given skin, the likelihood times the prior. And of course then the question came up of where does that prior come from? And again, we had to learn it somehow from training data. So we showed an example, this is from Gary Bradsky, of classifying skin color. At the end of the day, you would basically take this value and you would compare it to some threshold, and you would say, okay, if it's higher than the threshold, I'm going to call it skin, otherwise it's not. Like I said, it's sort of an old school way of doing it. They were the first methods being used in what's called pattern recognition. Pattern recognition is an entire field or discipline that looked at making these kinds of decisions. And one of the reasons was it was very easy to model this analytically, because you'd use things like Gaussians or whatever, or mixtures of Gaussians. And you could do this with modest amounts of data in a smallish, moderate number of dimensions. And because a lot of this was done before we had serious computers or before we had serious data, this was really important. But sort of in the modern world, or not even the modern world anymore, but the world 20 years ago, which I like to think of as being modern, because back then I was in my 30s, and I'm hoping that I'm not like really that old. Now I know, oh man, I'm old. Okay, fine. But in the modern world, there are some liabilities of the generative method. First of all, these days many of our signals are high dimensional, right? So we get some description of a signal, whether it's stock market data or whatever it is. I might have a feature space that's tens of thousands of dimensions, or at least many hundreds of dimensions. It's a very high dimensional vector. And if you actually want to represent a density in that high dimensional space, I wrote here that it's called sort of data hard, and what I mean by that is the thing becomes exponential in the number of features that you have, so you have to have sort of massive amounts of data. And even more, we tend to think of Google-style data as being massive. No. When you've got tens of thousands of dimensions, the amount of data you need to densely sample that is exponential, and we just don't have it. But there's even a bigger liability, okay? The bigger liability is that we don't actually care about modeling the whole class, right? If I've got sort of skin things and not skin things, you can imagine there's a whole bunch of colored pixels that have nothing to do with skin. I don't have to model that as not skin. We only care about making the right decision, so we should be modeling the boundaries, the hard cases, the cases where I'm not really sure. And when you do a general model of a category or of a class, you're worried about the vast majority of them, so the skin pixels, not just this boundary that's next to the non-skin ones. And I'm not even totally sure what it means to model non-class, non-skin pixels, because that's everything from, the pixels on colored shirts to the pixels on grass to the pixels on tree bark. It's kind of a weird, that non-skin's not really a great class. What I care about is find me the pixels that may be labeled as skin or maybe not. And finally, I'm going to give you a feature vector or a bunch of features that describe an instance, and we might not have any idea a priori which features actually are good for discriminating between the classes. So part of our building a classifier is essentially doing feature selection, right? We have to figure out what parts of the features or what parts of the signal are the sort of informative ones. And so for training a classifier, our generative model has no way of talking about doing that, but the methods we're about to talk about, which are called discriminative methods, inherently do that. For the rest of this and next, we're going to be talking about discriminative methods for doing recognition or classification. By the way, I'll probably use those words interchangeably, classification, recognition. Probably a little sloppy of me because we talked a little bit about the difference. I'm just basically talking about classifying something as being an A or a B, or even more precisely an A or a not A. Before we go forward, we're going to make some assumptions, okay? Our first assumption, we're going to assume that there's a fixed number of known classes, right? So I'm going to tell you there are 4 things in this universe you have to worry about. Now, they might be A's, B's, C's, and none of the above, but it's not like later I'm going to give you some D's, or later I'm going to give you some E's. No, I'm going to tell you the classes that exist a priori. So when I train this system and I'm defining the boundaries, I'm only worrying about the classes that you tell me in advance that I know about. The other thing I'm going to assume is that I've got plenty of data. I've got training examples that come from this class, and it might not be, shall we say, that data hard, I've got an exponential amount, but I've got lots of data, so it's possible for me to typically find points that tend to be, might get confused with some other class. For the conversations we're going to have today and the next time, we're going to assume an equal cost of mistakes. So it costs you just as much to call an A a not A as it does to call a not A an A. In fact, one of the methods will talk about the fact that some of the distributions might be quite asymmetric, right? So you might be looking for, say, faces. We're going to do that one. In an image, and you may know that most places in an image, in most images, are not faces. So you might take advantage of that fact in terms of how you search for them, but we're not going to worry about the relative cost. Remember that loss function between making the 2 kinds of mistakes. And the other thing is that we're going to assume is that, and this is actually good because it's true, it's always good to assume true things, we need to build a representation of each instance, so we're going to build a description, but we don't know a priori what features actually matter. So we're going to write down a whole bunch of things about it, each instance, and then we're going to train a discriminative classifier to make the distinction, the classification, and it'll have to figure out where the information is in the feature. All right, so that's a lot of assuming, but I'm good at making assumptions. There are essentially two parts to building a discriminative system. We have to build an object model that is a representation of each of the training instances. And here we're going to be talking